difficult questions. Let's start over here. So without further ado, I'll introduce my co-chair, Ray Riley, who will help me with these two presentations. We're going to start with subjective and biomechanical assessment of ride. There are many factors to consider when choosing a running shoe. How does the shoe fit? How does it look? Is the shoe comfortable? Comfort is an extremely important aspect, as discomfort can serve as a warning or a precursor to injury. However, the term comfort is not well defined, and research to date has failed to show any connection between comfort and any particular biomechanical variable. Ride is a term that is also used to describe the feel of a shoe. It can be found throughout the internet, from running blogs to the websites of footwear manufacturers. And although it's gaining a lot of popularity, similar to comfort, it is not well defined. Therefore, we established the following definition for ride. Ride, in heel-to-toe running, is the feel of the shoe as the foot transitions from the heel to the toe during the stance phase of gait. And it can be described as either being smooth or not smooth. We postulate that the plantar pressure will be a good, useful measure in order to quantify ride. And that ride might have something to do with how the center pressure actually travels across the foot. More specifically, the velocity or rate at which the center pressure travels may be a good indicator of ride. We are interested in the first 30% of stance, as that's the time that the center pressure will travel from the heel to the forefoot, and we propose that a lower peak velocity will be associated with a smoother ride. Research to date has showed that changing the stiffness of the midsole can affect the perception of cushioning of the shoe, as well as the rate of plantar flexion during the stance phase of gait. Now, these two results may be related to the center of pressure velocity. Therefore, we use shoes with different midsole stiffnesses in order to test our objectives. Our objectives were to relate ride to the center pressure velocity in the anterior-posterior direction, to relate ride to comfort, as well as relating ride to an individual's anthropometrics. And we established 4 hypotheses. First hypothesis is that subjective ride will be related to the center pressure velocity. Next, we expect that ride will be related to comfort. Following that, we expect the shoe that has a softer midsole will always have a smoother ride. And finally, we expect that ride will be related to an individual's anthropometrics. "13 male subjects took part in the study. They were all recreationally active, and they were tested under 2 shoe conditions. One with a soft midsole, and the other shoe with a stiff midsole. Plantar pressure, subjective ride, and comfort, as well as anthropometrics, were taken from each of the participants. And the task was over ground running. The shoes differed in both mass and the forefoot and rear foot stiffnesses, with the stiff shoe having a mass of approximately 20% more than the soft shoe, and stiffnesses that were approximately 25% more than the soft shoe. The age, height, and weight of all the individuals were taken, as well as the foot length, the arch height, and the arch length. And those were taken with a TechMed 3D foot scanner. Subjects ran on an indoor rubberized track at the University of Calgary, and they ran over 40 meters 4 times at a speed of approximately 3.5 meters per second in each shoe condition. Pressure sensing insoles measured the plantar pressure from the right foot at 200 hertz. And prior to beginning each running trial, subjects were explicitly explained the definition of ride and were asked to think about that while they were running. Because upon completion of each shoe condition, they're asked to fill out a subjective questionnaire. And they're asked to rate the ride and the comfort of each shoe independently. And this was done with a 15 centimeter visual analog scale. And the example of the question for ride was, how was the ride of the shoe? And the anchors were, it was the least smooth ride ever to it was the smoothest ride ever. To analyze the center of pressure velocity, 40 steps from each shoe condition were averaged and time normalized. This is the example of one exemplary subject, which clearly shows the difference in the peak velocity between the two shoe conditions. In this particular subject, they rated the shoe that had a lower peak velocity as having a smoother ride. So our first hypothesis was that ride, or subjective ride, would be related to the center of pressure velocity in the anterior-posterior direction. Our results showed that the shoe that was rated as having a smoother ride had a significantly lower peak velocity in the anterior-posterior direction than the shoe that was rated as having a less smooth ride. Our second hypothesis was that ride would be related to comfort. And our results show that the shoe that had a smoother ride was always rated as being more comfortable. On average, it was rated 3.5 centimeters higher on a 15 centimeter VAS. And so what we have shown here is that comfort is related to ride. And previously we showed that ride is related to center of pressure velocity. So we may have shown an indirect relationship between comfort and center of pressure velocity, which we believe may be a very exciting finding. Our third hypothesis was that a shoe with a softer midsole would always have a smoother ride. However, to our surprise, this was not always the case. In fact, 5 out of the 13 subjects had a smoother ride in the stiff shoe, or the shoe with a stiff midsole. And so what this tells us is that each individual has a unique solution, and that the ride of a shoe is not completely dependent on the construction of the shoe. So in order to investigate this further and to test our fourth hypothesis, which was that ride would be related to an individual's anthropometrics, we separated our subjects into two groups. The first group were the individuals that had a smoother ride in the soft shoe, and the second group were the individuals that had a smoother ride in the stiff shoe. And when comparing anthropometrics, we found that there was a significant difference in the height of the individuals, with taller people having a smoother ride in the stiff shoe. We also found a significant difference in the arch height of the individuals, with people having higher arches having a smoother ride in the stiff shoe. Now, up to this point, we overlooked the first result, where individuals who were taller had a smoother ride in the stiff shoe. However, recent evidence, particularly the presentation from yesterday by Jennifer Anderson and other groups, have shown this same relationship. So we believe it warrants further investigation in order to understand why taller individuals may have a smoother ride or prefer a shoe with a stiff midsole. However, functionally, we believe that the arch height may provide more of a mechanical explanation as to why we see the difference between the groups. And perhaps it might have something to do with the arch stiffness. And that is something else that we wish to explore further. So in summary, we have shown that the subjective ride is related to the center of pressure velocity in the anterior-posterior direction. We've shown that a smoother ride is associated with a lower peak velocity. Next, we showed that the subjective ride is also related to comfort. And we've shown the indirect relationship between comfort and center of pressure velocity. Our third hypothesis was a shoe with a softer midsole would have a smoother ride. However, we found that this was not always the case. In fact, 5 out of 13 of our subjects had a smoother ride in the stiff shoe. And finally, we showed that ride may be in part due to an individual's anthropometrics, and this may begin to explain why we don't see that relationship in hypothesis 3. So there are 2 avenues in which we wish to explore further. First is the applicability, and second is the functional relevance. So it is well known that footwear companies are trying to create a personalized experience for their customers in order to help them choose a shoe that is right for them. And we believe that this measure, or this variable of ride, may be used in that way. However, the current methodology that we're using is not suitable for use within a shoe store. The pressure sensing insoles we're using require a lot of equipment, they may be cumbersome, and require a lot of post-processing. Inertial measurement units, on the other hand, are small, they're portable, they can provide rapid feedback, and they can be placed all across the body. Currently, we are conducting other experiments that are looking at the use of IMUs over these different areas of the body to see if they're able to detect ride. And let me show you an example of one of the studies that we're doing. So this graph represents the vertical acceleration of an IMU that is placed on the hip. The solid line represents the acceleration as the subject runs in the soft shoe, and the dotted line represents the acceleration as they run in the stiff shoe. Now in this case, the subject found that the stiff shoe, had a smoother ride. And if we look at the acceleration, we can note that it has a much lower acceleration than the soft shoe. Here's another subject from the same study. Again, the solid line represents the soft shoe, and the dotted line represents the stiff shoe. And in this case, the subject found that the soft shoe had a smoother ride. And looking at the acceleration, it too had a lower acceleration. So even though this is only two examples, we are beginning to show a nice relationship with this IMU, and perhaps with further research in other studies, we will be able to create a nice model that we can use that can be implemented within a shoe store in order to help us determine the shoe that is right for the customer. The second aspect in which we wish to explore is the functional relevance. Now, in the results, we showed that there was a significant difference in the arch height, and we believe it may have something more to do with the arch stiffness. So we proposed to generate a mechanical model that includes both the arch stiffness and the midsole stiffness in order to better understand the function of each of those stiffnesses independently. And hopefully we will be able to generate an output, such as the graph that was drawn by hand on the right, so that we can use this in order to help determine an optimal ride based on an individual's arch stiffness and a shoe's midsole stiffness. So in conclusion, we believe we have a very exciting variable in ride. We've shown that it's related to the center of pressure velocity, to comfort, as well as an individual's anthropometrics. And finally, we've provided some insight into a potential application for use of this variable in order to help individuals find a shoe that is personalized to them that will give them the smoothest ride possible. Thank you. Thank you. We will welcome your questions.
Great study. Obvious omission with the anthropometry, body mass. Did you look at it?
Yes.
And what did you see?
There are no differences in the body mass. So it was just the height that was different.
What range of body mass do you have? You've got 13 people. But the stock down from experience, you get a 90 kilo person, put them in a soft shoe, they're going to bottom out and not find that comfortable, and a lighter person is going to like a stiffer, more responsive shoe. Got any thoughts on potentially future, how big a sample size with a larger range of body mass might show you something, maybe?
I think that's a really good idea. We are conducting other experiments, so we have not selectively chosen subjects based on their body mass or height. This is just something that we found, but I think since we have found this result and since there are other studies that are showing this, I think that it is very important to start looking into this further, and perhaps choosing different body masses may be one of the avenues that we take in order to look at that. I think that's a really good point. Thanks.
peak pressure analysis or some other variables?
Yes, we did do peak pressure analysis. I unfortunately don't have any prepared slides for that, but we did not see any differences in the peak pressure analysis. And we were
Related to different individuals.
Sorry, could you repeat that?
Peak pressure analysis in comparison between
No, we didn't actually do that, but I think that would be really important to look at to see if there are any systematic differences between the individuals, to see if that may be one of the reasons why they have a smoother ride in one shoe versus the other. Thank you.
So Evil would agree with me that when you ask people multiple questions about their perceptions, the responses tend to be highly correlated with their overall preference. So how did you control your experiment when you're actually asking people for two different perceptual responses? How do you control your experiment so that you don't get an artifactual correlation between comfort and ride?
That's an excellent question. So it was all in a way that we asked them to subjectively evaluate ride. When they were filling out the questionnaire, we explicitly told them to think of both things independently and not to rate one based on the other. However, I do completely agree that since we were asking them in the same questionnaire, we were having them think about ride the entire time, that may have been a confounding factor as to how they rated the comfort.
Do you always, asking them to be objective never works, unfortunately. So did you randomize the order of the questions, or was it always ride first and then?
It was always ride first.
Yeah, okay. Which risks biasing the responses. They want the second response to be consistent with the first to make you happy and all that kind of stuff.
Yeah.
Okay, thank you.
Thanks.
So you did 4 40-meter trials. Were they fully rested before the next trial?
Yes.
So I was wondering, how do you think fatigue? Because in a normal setting, they would run probably a longer distance and be a little more fatigued. How do you feel like fatigue will start to factor into the perceptibility of ride?
That's a very good question. We gave the subjects breaks in between each running trial. They had about 30 seconds. When they finished the 40 meters, they would walk back and they could rest a little bit until we got the equipment set up. So no one ever reported ride. Also, we randomized the shoe testing, I guess, between subjects. And in between shoes, they had approximately 5 minutes in order to rest as well. So I don't think that there was any effects of fatigue.
I can claim fatigue would be important for people who are using it in everyday context. So how do you think fatigue may change your ride?
Yeah, I completely agree. As you run, you're going to have differences in your anthropometric. Your arch may fall when you become fatigued. There's going to be a lot of differences. I'm not really sure how that's going to affect the ride, but right now we're looking at something that will be very simple to implement within a shoe store, and I don't think we would experience fatigue, and hopefully the initial sensation of this will help them guide to choose a shoe that's right for them. I don't know. I think that's something to consider moving forward with this variable. Thanks.
Okay, we'll just take 2 more.
Wolfgang Potterström, Sporting University in Cologne. I might have missed it. Why do you think the lower center of pressure velocity is related to higher perceived comfort? Is there any functional mechanism or explanation?
We set out to look at the lower velocity just based on this idea of ride. So when we see this term being used on the internet, it's always the shoe had a really smooth ride. It is always associated with a favorable sensation, and that's why we thought that when we started to look at ride, we should also think about how that might be actually related to comfort, because they're used very similarly on the running blogs. So it was nothing more than just that association, which is why we figured that the lower velocity would be associated with comfort.
Just purely speculative, could it be that it has to do with the lever arm of the ground reaction force, that it travels quick or less quick and creates a different initial plantar flexion moment, which might be perceived uncomfortable if it's very quick?
Yeah, that definitely could be one of the reasons why it would be deemed as uncomfortable. I agree.
Timo Bargon from Adidas. Adding a bit to the previous questions before, how would you describe comfort and how can you distinguish between comfort and ride? And maybe they see it's the same, so they don't judge it as the same value actually, as the same parameter.
That's an excellent question, and I did not prepare a definition of comfort at all, but the funny thing about comfort is it doesn't really have a definitive definition. And I think everyone in the room will have a slightly different idea of what that means to them. And so we didn't try to influence our subjects into thinking that comfort meant one thing alone. We just tried to keep it very vague in order for them to use that term in order to relate it to themselves. I don't know, perhaps some people will think of comfort and ride as the same thing. Other people might think of it very differently. But yeah.
In the interest of time, I know there's more questions where we're going to move on. I encourage you to have a beer and discuss it more later if you want the conversation going. Thank you very much.
IMU って何やった？ヒップあれはですね、感性センサーで、イナーシャル、センサーのことなんで、加速度のですけど、はい、の運動中のグラフが結構ライトと近いっていう話だと思うんですよ。星ですね。結局それだけで分からんかっちゃう話ですよ。あれと因数がまだあれだからっていう話。
Laceration injury risk test protocol.
Thank you, Ray. So my name is Woody Wildstone. I'm from the Centre for Sports Engineering Research, which is at Stratford Harvard University in the UK. Looking at laceration injury risk, we're looking from studded footwear or pleated footwear review, which is the American term, in rugby union. The reason why I'm looking at rugby union is because this is a sport with a high injury history. 91 injuries per 1,000 play practice. This means that a professional rugby player statistically can get expected to get injured 1 in 8 matches, or in a different way, 2 injuries per match per team. We did a systematic review and found that skin lacerations account for 5% of these injuries. And stud technique design has been identified as a potential cause of injury. When I talk about injuries in rugby union, I mean an injury which causes a player to miss a subsequent training session or match. So this is not something to take quite lightly. I have some examples of laceration injuries, but if you don't want to see it because it's a bit gruesome, then you don't have to. So on the left here, we have professional rugby player Nick Schoenert who got trampled on during a match, so the stud lacerated his cheek. And on the right, we have an amateur player who gets stamped in the rib. What we do not know is what type of studded footwear is more likely to cause laceration injuries. So therefore, the aim of my study was to develop a mechanical test method to quantify laceration injury risk of stud designs. Stud designs have been through a little bit of evolution over the last couple of decades. So probably the most well-known and still commonly used stud design in rugby union is the aluminium rounded stud. And in the 90s, when injection molding allowed us to make the full outsole out of one material, we got different stud shapes, and the bladed stud is probably one of the first examples of this. After that, we innovated our stud footwear even more, and we got hybrid or mixed-sole plate stud designs, which means they have a combination of screw-in studs and molded studs. And in February of this year, World Rugby approved these new screw-in studs, which are like a T-shaped aluminium stud design, despite comments about their more pronounced edges. With 3D printing becoming increasingly popular. We've been talking about personalization of footwear. We can now actually tailor the outsole design to the specific needs of a player. But what we do not know is what the influence of these different shapes and materials are on the laceration injury risk. World Rugby, which is a governing body of rugby union, has a set of tests in place to test footwear, and they consist of a Part A and a Part B. Part A is aiming to replicate stamping, and Part B is aiming to replicate breaking, and I'll come back to those terms a little later on. So Part A has a stud attached to a 8.5 kilogram mass, impacting from 50 millimeters high a skin and muscle simulant. Part B has a stud attached to a pendulum arm, again impacting a skin and muscle simulant, but with an unknown mass or height they don't specify. The validity of this test method has not been proven because the test method is actually not based on impact conditions representative of injury scenarios in the field of rugby. It is based on a heel striking impact of running, to be precise. So at the moment, the World Rugby regulations are not mandatory for manufacturers to follow, which leads to the referee being responsible for checking the studs of every player before a match. He does this by lining them up and visually assessing what type of studs they're wearing and running his hands over them to find any sharp edges. And that does mean that you don't actually know as a rugby player whether you're allowed or not to play with a new type of stud, because you're like, oh, it depends on the referee if he's going to allow it or not. So having a test method in place can provide clarity and guidelines to both manufacturers who are here in the audience, but also for the consumers, for the players that are going to buy the boots. A good method will allow innovations instead of footwear, because we want innovations to happen, but will only limit excessive or unnecessary injury risk. So the way we've got about developing this more representative test method is to first look at what kind of game scenario in rugby is actually causing laceration injuries. Then we replicate this game scenario in the lab, do a biomechanics study, and find out what the kinetics and kinematics are of such an impact. Then we translate this into test parameters for a mechanical test design. So to find out what the game scenarios were causing laceration injuries, we did a questionnaire study. We asked 191 players if they ever got injured, and 70% said that they had a laceration injury at least once during their career, severe enough for them to leave the field during a rugby match or training session. 50% of these players stated that purposeful stamping in the rug was the event that caused their injury. And I have a little example of what that might look like, which is a video. So if you can follow player number 1 there, who's going to stand on the player on the floor. It's only 7 seconds. There he is. The interesting thing about this video is that you can see the referee here giving a penalty because the person on the floor wasn't rolling away. He's not actually penalizing the illegal action of stamping in the rug. So we replicated this stamping scenario in the lab, and we didn't use a player on the floor, we used a crash test dummy for ethical reasons. So we asked participants to set up a 1-versus-1 rugby scenario and measured their 3D foot kinematics with 2 high-speed cameras, so we could have the foot movements before and during impact. And then we measured the force underneath each individual stud with a set of pressure sensors. We found that this stamping motion could best be described in 2 separate phases. So first we have the initial impact phase, and then we have a braking motion phase. If you compare the initial impact phase to part A of the test method, which was aiming to replicate stamping, we find that the force underneath each stud equated to 1.2 kilograms, whilst the current method is actually stipulating 8.5 kilograms. On the other hand, we found a higher inbound velocity, so our participants were on average stamping with 4.3 meters a second, whilst the 50 millimeter drop height in free fall would only result in an impact of 1 meters a second. Next to that, we're also talking about linear movements. This wasn't a very linear movement. The velocity of the inbound velocity had actually an inbound angle to it, so it wasn't a directly vertical impact. If you then compare the impact energy of the higher inbound velocity but lower mass to the higher mass but lower velocity, we found that our participants were stamping on average with 9.5 joules, whilst the current regulations stipulate 4.2 joules. Now, if you look at the raking motion, I compared it to part B of this test method, but this test method didn't have a specified mass and height. What we did find was that during this raking motion, if we look at the stud, which was exerting the highest pressure, this was on average 132 newtons over the space, and the foot was accelerating from approximately 0 to 1 meters a second. We used these parameters to then design a new mechanical test method. I've only presented to you the averages of all these impact parameters, but we found the whole range. So this test design is designed to replicate the whole range of the impact parameters. What we did was we also split it up in an initial impact and a braking phase, just like what we saw in the biomechanics study. During this initial impact phase, you can change the inbound velocity by changing the drop height of the pendulum arm. So the stud is impacting a skin simulant here. You can change the impact mass by these weights. You can change the inbound velocity angle by putting it at a different pivot point. And you can also change separately the angle at which the stud impacts the skin. After test 1, we have to move the stud and skin simulant to test 2, which performs a controlled brake. In this test, the braking force can be controlled by these weights. The stud angle can again be set over there, and the velocity is controlled by a spring damper system, so that spring's there and a damper there. After you have impacted the skin simulant on these two tests, you need to assess the damage done to the skin simulant. And that's how we quantify injury severity. What I want to do in this test method is first scan the simulant before impact and then also after impact, and I can overlay these two 3D scans and calculate a color difference map. In the color difference map that you can see there, green means no difference and red and yellow means high difference. This method allows us to calculate wound parameters such as wound surface area and wound volume. So to summarize, we found that stamping in the rug causes laceration injuries in rugby union. And when we took this injury scenario to the lab, we found that the current World Rugby Test method does not represent this injury scenario. Having these test methods in place now, currently in the regulations, could mean that we could be banning studs which are actually safe to play with, because it's not actually a valid method, or it could mean that we are allowing studs which have a heightened laceration injury risk. Therefore, we developed this new mechanical test method, and we hope that implementing this method will reduce the amount of injuries that we see in rugby union. So, in the future, I have just finished building these two rigs in the workshop, and I will be testing the repeatability of the test method, and I need to identify which skin simulant I'm going to use. And then I want to finish this project by testing a range of stud designs which are currently on the market on their laceration injury risk. In future, we would also like to investigate what the influence of wear is, because wearing studs down when you walk from the changing rooms to the field has been identified as a heightened laceration injury risk. This test method is not just applicable to rugby union, it can be very applicable to football, to American football, Aussie rules. But in order to use the same test method, I would recommend doing a extra biomechanics study to identify the impact parameters specific to these field spots. That's my presentation.